Hi, I'm Max, and together with Lou, we're going to take on a tour of mesh shaders in the AMD RDNA 3 architecture. We're first going to take a look at some example uses of mesh shaders. Then we're going to explore how you can optimize your mesh shaders, and at the very end, we're going to take a sneak peek into the future of mesh shading. But before that, let's quickly recap how we got here. So for the past decade, the geometry pipeline on GPU looked like this. We had an input assembler feeding into a programmable vertex shader, which would transform your vertex positions. Those transformed vertex positions would then get assembled into triangles, and those triangles would be rasterized on screen. If you then want to render a triangle mesh, you first had to split it into a vertex buffer and an index buffer, supply both to the input assembler, and that would take care of invoking the vertex shader. Now, this reliance on a fixed function input assembler brings some key limitations with it. For example, there are only a handful of formats supported for the index buffer. Secondly, you're also going to notice that the vertex shader operates on a per vertex basis, meaning that we can't actually create, modify, or delete any triangles in this stage. And our input mesh looks more like a point cloud than an actual triangle mesh. Of course, you could take the detour for the tessellation and geometry shader stages, but those will only give you limited access to triangles and have some further problems of their own. So the only component we're actually interested in here is the rasterizer. And ideally, we'd like to send triangles directly to it. And that's exactly what the mesh shader allows us to do. The mesh shader replaces all the prior stages of the geometry pipeline with one new shader. And to send triangles to the rasterizer, the mesh shader has access to an output array of vertices and indices, and those indices then define triangles based on the vertices. The mesh shader programming model is very similar to the ones of compute shaders, and multiple mesh shader threads are organized into thread groups. We can then invoke those thread groups with a three-dimensional dispatch grid from the CPU, very similar to how we launch compute shaders today. Now, those output arrays are then shared across the entire mesh shader thread group, meaning that in this case up to 128 threads can work together on creating the output. And we'll hear more on how to optimally write to those arrays later on. For now, let's focus on how we can get data into our mesh shader. If you take a look at the graph below, you'll see there is no longer an input assembler in our pipeline. So that means we'll need to take care of this ourselves. Luckily, as the mesh shader employs a compute-like programming model, we can simply read from any number of buffers we like. And those buffers can have any format we like, meaning we get complete flexibility over how we design the input. Now, obviously, a single mesh shader thread group can't run an entire mesh by itself, and the number of vertices and triangles it can output is limited to 256 each, meaning that if we want to render a larger mesh, we first have to split it into smaller parts, often referred to as meshlets. Now, the exact way and parameters of splitting the mesh into meshlets is highly customizable and can be optimized to your needs, but we'll hear some general guidelines on this later on. For now, let's focus on what we can actually do with the mesh shader, apart from rendering those meshlets. Well, given the ever-growing geometric complexity of modern AAA games, we might be interested in compressing the data whilst rendering it. So, say in this example, our vertices are comprised of a vertex position, a normal, and a texture coordinate, and we're using 32-bit indices to define triangles. And a normal mesh, this will give you a 40-60 split between the index buffer and the vertex buffer. In this case, they nicely add up to 100 megabytes. So let's see how we can compress this. We said before that we want to use meshlets. And to keep things simple, we'd like to have a local set of vertices per meshlet, meaning that we have to duplicate every vertex that's at the border between two meshlets. Now, duplicating vertices means we now have more vertices and our vertex buffer gets larger. So, not a great start to compression. But we can easily redeem some buffer size if we just quantize all the vertex attributes. Now, attribute quantization is nothing new and can even be applied to the vertex shader pipeline. In this case, we chose a 18-bit global quantization grid. And there is one trick here we can do. As our meshlets are generally smaller than the entire mesh, we can store the data locally per meshlet and reduce the number of bits actually needed to store the information to somewhere in the neighborhood of 16 bits, while still being able to guarantee crack-free dequantization of the attributes. Now, all these parameters here, like the 18-bit global grid, is completely adjustable to your needs and only serve as an example. So here, we've now reduced the vertex buffer size down to just 37 megabytes, meaning that the index buffer is now the largest part of our mesh. So let's see how we can address this now. Again, index buffer compression itself is nothing new, and there are, for example, countless techniques described in his 2012 dissertation. But most of them couldn't be applied to the traditional vertex shader pipeline, as, for example, I mentioned before, the input assembler is a limiting factor here. So, in this joint work with Coburg University, I'm going to show you how we can bring some of these advanced index compression techniques described here to mesh shaders. So, if we take a look at a single meshlet, the first and probably most obvious thing you're going to notice is the index format we've been using up until now. We said before that we're using 32-bit indices, but we're using meshlets now, and we know that our meshlets can only contain 256 vertices maximum. So that means we can easily swap this out for 8-bit indices. Now this will already reduce the triangle size to just 24 bits, or in other words, give us a 4:1 compression ratio. Now even without the vertex compression or vertex quantization I mentioned before, this would already be smaller than the input buffer. But we can do even better here. Next, we can compute a generalized triangle strip through our meshlet. Now typically this would be something that's difficult to do, but again, we're only dealing with 256 triangles max, so we can even compute the mathematically optimal triangle strip, meaning the one with the least number of restarts in a reasonable amount of time. To encode the triangle strip, we'll need a 1-bit code indicating whether the triangle strip moved left or right, and then we'll need an 8-bit index for the new corner. Now in total, this will give us 9 bits per triangle, or a compression ratio of 10:1. We can then decode this triangle strip in a mesh shader using simple bit operations. If you take a look at the index buffer that we've created here, you notice that a lot of indices are following this ascending pattern. And of course, we can exploit this for even better compression. We can replace all these indices with a marker indicating whether they follow the ascending pattern, and then only explicitly store the ones which do not follow the pattern. Now this is very similar to what Epic Games uses in their nanite compression, but in this case all the decompression and rendering is happening inside a mesh shader, in a compute pre-pass. So our updated index buffer now contains a 1-bit code for the ascending pattern, the 1-bit triangle strip code from before, and every now and then we'll still need an 8-bit index. But averaged across the entire meshlet, this will only account for roughly 3 bits per triangle. So in total we're now down to just 5 bits per triangle, or in other words a 16:1 compression ratio on the index buffer. Decoding of this ascending pattern is again done in the mesh shader using simple bit operations. Now this brings us to the end of the index compression, and in combination with the vertex quantization, we've now managed to reduce the buffer size to less than 40% of the input's buffer size. Next, let's take a look at performance of all of this. To evaluate the performance of the compressed mesh shader pipeline, we'll take a look at 2 fairly large triangle meshes. We'll compare it against a regular vertex shader pipeline and a much simpler mesh shader pipeline without any compression. Now keep in mind that the decompression of the triangle strip and the dequantization of all the vertex attributes is running for every meshlet in every frame, and we'll still be able to outperform the regular vertex shader pipeline by about 9%. This means that you can now store and render compressed data directly on the GPU without needing any compute passes to decompress it first. If this sounds interesting to you, keep an eye on gpuopen.com or follow us on one of our social channels linked below, as we'll have a blog post up on this soon. Now, 9% faster than the vertex shader pipeline already sounds pretty impressive, but what if I told you that we can go even faster? Up until now I showed you that the mesh shader pipeline looks like this, but there is one shader stage I omitted, and that is the amplification shader. The amplification shader sits between the 3-dimensional dispatch grid from the CPU and the mesh shader, and as the name implies, is used to amplify the overall workload. To do this, the amplification shader has access to the same dispatch mesh command that we used on the CPU to launch mesh shader work, but in this case on the GPU. This means that every amplification shader thread group can launch an entirely new 3-dimensional dispatch grid of mesh shaders. In addition, that thread group can pass a payload along to all subsequently launched mesh shaders. You can think of this payload as updating constants in your root signature in between dispatch mesh calls on the CPU. But now everything is happening on the GPU. So while this launching mesh shader work from the GPU might sound like the fastest way to create a TDR, we're actually here to make a renderer faster. So let's see how the amplification shader can help us here. One way to go faster is to simply just render less geometry. And one way to do that is to use a level of detail system. Now, with the amplification shader, we can dynamically select the level of detail to render on the GPU. To do this, we can launch one amplification shader thread for every instance we want to render. Then that thread can determine the appropriate level of detail, for example, using the distance to the camera. Next, we'll need to sync up with all the other threads in the same amplification shader thread group. Remember, the entire amplification shader thread group dispatches the 3-dimensional dispatch grid. We can use wave intrinsics to sum up the required number of mesh shader thread groups we need to launch and dispatch them. In the payload, we can then pass some information on which level of detail each mesh shader thread group needs to render. Now, a second way to go faster would be to not render anything that's not visible, or in other words, to perform culling operations. Now, typically, you've probably heard of triangle culling, but in this case, we're doing Meshlet culling, so culling on a way coarser level. The concept here is pretty similar to the dynamic LOD from before. We're dispatching one amplification shader thread for each meshlet we want to render. Then we test its visibility using, for example, a bounding box, bounding sphere, or some other ways of determining visibility. Then we again need to sync up with all the other amplification shader threads in the same thread group, sum up the number of meshlets to render, and then dispatch the mesh shaders. And that's exactly what we're going to apply to a compression example from before. Now, in this case, we opted for cone culling, which you can think of as basically backface culling, but on a per meshlet level. Now, switching to the render times with culling, you're going to see two performance behaviors emerging. For non-closed meshes like the rock on the left, there are simply no back-facing meshlets to cull, and you're going to pay a small overhead for running the amplification shader. But for closed meshes like Lucy on the right here, you can expect to cull 30 to 40% of all your meshlets, giving you a nice 40% boost in performance. Of course, you can extend this even further with additional culling methods like frustum culling. So up until now, we've been focusing on rendering triangle meshes, so directly replacing what the vertex shader pipeline could already do for us. But a lot of artists prefer to model their meshes using quads. As we said before, we have complete control over the input to a mesh shader, so we can also store quad meshes in our input buffer. But the rasterizer still demands triangles from us. We can easily fix this by simply converting each quad into two triangles in a mesh shader. But there is one problem. You see, if you convert a quad into two triangles, you'll still be using barycentric interpolation in the pixel shader. That means you're only interpolating across the 3 corners of the triangle and not all 4 corners of the quad. If you now take a look at the topmost triangle here, you can see that there's no idea what its other half is doing because it's missing the attribute values from that 4th corner. The correct way to interpolate here is to use bilinear interpolation. This means we taking into account all 4 corners of the original quad to evaluate the attributes. But the question here is, how do we actually get that 4th corner into the pixel shader for interpolation? And mesh shaders can actually help us here. In addition to the output array of vertices which define attributes for each vertex, mesh shaders also allow us to define per primitive attributes with an additional output array. We can then use these per primitive attributes to implement bilinear interpolation. In addition to that, the primitive attributes also offer greater flexibility overall, allowing us to more efficiently pass data between the mesh and pixel shader stages. In this case, we can even split some of the computation between the mesh and pixel shader stage, further increasing the efficiency in data transferred. This increased efficiency can also be seen in the performance, as the mesh shader is able to outperform comparable implementations using the tessellation and geometry shader stages. So, even with the quad example we just seen, we are still loading vertex information from a buffer. But we said before that modern games often have quite high geometric complexity. And this, for example, also extends to vegetation. So what if instead of loading data from a buffer, we directly compute it on the mesh shader? Well, the mesh shader gives us complete freedom over how we output the vertices, meaning that, for example, we can replace the loading vertices from a buffer with some computation based on some splines. You can, for example, procedurally compute some control points based on a base position, move those control points around using some sine and cosine waves, and generate a nice patch of waving grass, all in a mesh shader, without needing any input data. Now, if you want to turn this single patch of grass into a meadow, you could, for example, dispatch a lot of them from the CPU and place them all around your scene. But you can take the concept of procedurally generating it even a step further by combining it with an amplification shader. If you supply the amplification shader with the camera view frustum and, for example, a height map of your scene, you can sample positions on that height map in the amplification shader and only launch grass patches in the visible area. This way, you can turn a single patch from before into a nice waving meadow, all on the GPU. In this case, there is only a single mesh shader running here to generate all the grass, and that mesh shader is generating over 50 million triangles in less than 3 milliseconds. If you're interested in this, be sure to check out our blog post linked below. Now this also concludes the example section of this talk, and we'll now hear some performance considerations from Lou.
Hi. I will talk about performance considerations when using mesh shaders. When talking about performance considerations, we need to look at the whole mesh shader pipeline. I will start with the Geometry engine, because the Geometry engine is responsible for launching mesh shaders. Then I will talk about the mesh shaders themselves, and specifically I will talk about how mesh shaders export their vertices and primitives to the rasterizer. Lastly, I will also talk about amplification shaders. They are optional, but if you decide to use them, you should know a few things to make sure that you actually benefit from them. But let's start with the Geometry engine. And actually let's start with the Geometry engine and what it's doing for vertex shaders. Because for vertex shaders, the Geometry engine has a vertex reuse cache. It's an optimization to avoid reshading vertices unnecessarily. It ensures that a wave only processes unique vertices. Existing asset pipelines, they try to take advantage of this vertex reuse cache and optimize the assets so that they make the best possible use of this cache. The Geometry engine relies on the fixed input structure of the vertex shader to fill in this vertex reuse cache. Unfortunately, when you're using mesh shaders, the input data is user-defined. So the Geometry engine has no way to know how to interpret the input data. This means that when you're using mesh shaders, there is no vertex reuse cache. So all the existing optimizations of the asset pipelines will not help with mesh shader performance. Also, if you have a direct vertex shader to mesh shader translation, you might actually observe a drop in performance because of exactly this reason. The vertex reuse cache is not used for mesh shaders. So if you use the vertex buffers and index buffers that you use for vertex shaders in your mesh shaders, and you use the indices to pull the correct vertices and then process them, you might end up processing more vertices than you would have with using vertex shaders. So what should we do when you're using mesh shaders? Well, this vertex reuse cache optimization needs to be done manually. And usually this is done already doing meshlet generation. So how to represent the meshlet, again, is totally up to you because it's user defined. But there is a very common way to represent meshlets. We've seen this already in this presentation when Max talked about compression. There he had a per meshlet index buffer and a per meshlet unique vertices buffer. The index buffer encodes the primitive connectivity. And the unique vertices buffer, well, it contains all the vertices that are needed in this meshlet. There are some limits from the specification. So a meshlet can have up to 256 vertices and up to 256 primitives. But this also means that when you're having mesh shaders, you can have batches of unique vertices of up to 256, which is much more than the batches of unique vertices that are created by the geometry engine, because the vertex reuse cache typically only accounts for about 32 vertices. Of course, when you're using mesh shaders, you still have to duplicate vertices. And the vertices that needs to be duplicated are the border vertices, because these vertices end up in multiple meshlets. This is also the reason why when you compare the vertex buffer sizes themselves, so the vertex buffer of your vertex shader and the total vertex buffer of your mesh shader, the vertex buffer of the mesh shader might be larger. We've seen this in Max's example already. However, the amount of vertices that are getting processed might be less when using mesh shaders because we have less vertex duplication. So here you have a potential advantage when using mesh shaders. However, how well this works out in the end highly depends on your meshlets and how they are generated. So this topic about meshlet generation is very complex, and it's also very content specific. Generally, there's still a lot of room for research. But commonly, there are 3 metrics that you should consider when generating your meshlets. The first one is the number of border vertices, due to the reason that I just explained, because border vertices have to be duplicated. So you want to keep this number as low as possible. You also want to have a small size of the bounding box, because if you have a small bounding box, this helps with culling, and it also improves the quantization position. Lastly, you also want to have triangle strips, so topologically connected triangles. This can also help with compression. However, if you, for example, only focus on triangle strips, you might end up having even less good performance because it can have side effects. So if you only focus on having triangle strips, you might end up having a large number of border vertices or a large bounding box. So the key here really is to find a good balance between all 3 metrics. So I talked about what the geometry shader is not doing for mesh shaders. Now let's talk about what the geometry engine is actually doing for mesh shaders. So it does determine the thread ID for each thread, which is the same as the equivalent for determining the vertex ID for each vertex. It also prepares the shader export and it initiates the launch of the shaders. Since it doesn't do any vertex reuse cache optimization, it has less work to do for mesh shaders. And this results in a faster launch rate for mesh shaders. So here you have another potential performance advantage when using mesh shaders. let's have a look at what the Trinity engine is doing when preparing the shader export. In this step, it's allocating enough space for the maximum number of exported vertices and primitives per thread group. These maximum numbers are defined in your shader code. So for this example code snippet on the slide, the Trinity engine would allocate enough space for max triangles primitives and max vertices. The size of the export buffer is finite, and if the export buffer is full, no new waves can be launched. This also means that these numbers that you are setting in your shader can actually limit the maximum occupancy of your mesh shader. Generally, the size of the export buffer is designed such that an average mesh shader workload can reach rasterizer triangle throughput. So it's totally possible that an occupancy of about 25% is already enough to reach the triangle throughput limit. If you have very complex mesh shaders though, you might see a higher occupancy of about 50%. And these complex mesh shaders, they actually tend to get limited by the available memory in the shader export. So for these shaders, we recommend to set the number of max triangles and max vertices as low as possible. And then of course, the occupancy of your mesh shaders can also be limited by the number of VGPRs that are used, the size of the allocated group shared memory, and also by the launch rate. The launch rate can become an issue if you have a lot of really tiny mesh shader draw calls that are not doing a lot of work and also not producing a lot of work. The occupancy can be seen in RGP under the wavefront occupancy tab. The mesh shader will appear as a Trumpty shader and will be also colored as such. The details can be found under the Trumpty shader tab, but also under the vertex shader tab, so the details will be just duplicated. Of course, trying to increase the occupancy only might help if you're not limited by triangle throughput. An indicator for a mesh shader being limited by the rasterizer throughput is the high export instruction latency, particularly on the first export instruction. You can see that if you, again, take an RGP capture, then you go to the instruction timing tab and you look at the first export instruction. There, if you see a high export instruction latency, this means that you might be limited by rasterizer throughput. So I talked about mesh shaders themselves already a bit. Let's talk more about them. Mesh shaders, they are a lot like compute shaders. So you use num threads to define the thread group size, and then you use the thread ID to read from the input buffers and to write to the output buffers. These buffers are shared, so any thread can read and write to any index. However, unlike compute shaders, the vertices and primitives are exported to the shader export. So in the ISA, you will see the export instructions. And this is also what the Trinity engine is allocating space for. Vertex attributes are exported by a regular buffer stores on RDNA 3, and on RDNA 2, the export instruction is used. On RDNA in general, so regardless if it's 2 or 3, the order of primitives and vertices in the shader export is defined by the order of threads in the thread group. This means that thread n exports vertex n and primitive n. This is also how vertex shaders export their vertices. To make it 100% clear, I made this small diagram on the slide. Here you see that thread 0 exports vertex 0, thread 1 exports vertex 1, and so on. If you want to write mesh shader code that follows this guideline, you use the thread ID of your mesh shader thread to export the vertex and the primitive. Of course, no one forces you to write mesh shader code like this, because mesh shaders actually allow any thread to write to any index in the output buffer. So you can have a mesh shader that does export like this on the slide. Unfortunately, this export strategy doesn't comply with the order of primitives and vertices in the shader export. So we have to fix this. And with V, I mean the compiler in this case. because the mesh shader itself is valid. The specification allows this. So the compiler needs to fix this, and it's doing this by using group shared memory as a staging buffer to re-swizzle the vertices such that in the end thread n exports vertex n and primitive n. This swizzling via group shared memory can be seen in the ISA. So in this example code, you can see that just before exporting the primitive data is loaded from group shared memory. You can also see that the group shared memory utilization increases under the hardware utilization segment in the instruction timing tab of RGP. And for this particular screenshot, I actually used the mesh shader that doesn't use explicitly group shared memory. So all the group shared memory usage of this shader was inserted by the compiler to fix the export indices. Mesh shaders also allow a thread to export multiple vertices and primitives. So you can have a mesh shader that exports thread ID and thread ID plus 8, for example. On RDNA 3, this is achieved by a wave-wide offset to the export instruction. So the code on this slide is actually natively supported on RDNA 3. In some cases, the compiler might still choose to use the group shared memory as a staging buffer. On RDNA 2, it's a bit different. And this is actually the only slide I have in this presentation that's specific to RDNA 2. And I added this because the performance characteristics on RDNA 2 are quite different for this specific case, because RDNA 2 does not have a wave-wide offset. This means that a thread can only export one vertex and one primitive max. So what's happening is that shadow threads are launched. And these shadow threads, they don't do anything except exporting. So in this case, you not only have the overhead of group shared memory to do the swizzling, but also the overhead of additional threads that are launched. To conclude the export section, we recommend that thread n exports vertex n and primitive n. And if multiple vertices and primitives are exported per thread, we recommend to use a wave-wide offset. Otherwise, the latency might increase, and this can decrease the triangle throughput. In our experiments, we've seen, depending on geometry and mesh shader complexity, a difference of up to 15%. Also, group shared memory usage is increased, which can have the side effect of limiting the maximum occupancy of your mesh shader. Also, you can use group shared memory explicitly in your mesh shader code to exchange data between threads within a thread group. However, group shared memory is limited, and also, as already mentioned, it can limit the maximum occupancy of your mesh shaders. So if you use group shared memory and then the compiler uses also group shared memory, the occupancy of mesh shaders might be limited more than you initially anticipated. Additionally, pixel shaders also use group shared memory, so their occupancy can be affected as well. And in very extreme cases, you might even spill to global memory if there is not enough group shared memory available. We talked about export and how you should do it, but this actually also depends on your Meshlet configuration. So which Meshlet configuration do we recommend? Well, if you look in the internet for Meshlet configurations, you will find two recommendations. One is that you have a Meshlet with up to 128 vertices and up to 256 primitives with a thread group size of 128. The other recommendation is that you have a Meshlet with up to 64 vertices and up to 126 primitives. You can also use 128. On AMD it doesn't really matter, but the recommendation will be 126. And the thread group size is 64. So the first observation that we can do is that both recommendations have more primitives than vertices. And the reason is that the main compute workload is typically vertex transformations. So you don't want the number of primitives to be the limiting factor, but the number of vertices. The second recommendation is that the thread group size is equal to the maximum number of vertices. And this is again because the main compute workload is typically vertex transformations. So you want to ensure that you have one thread processing one vertex. If this is not possible for whatever reason, then you should try to divide the maximum number of vertices evenly across the threads. So the difference between these two recommendations is really that one suggests larger meshlets, while the other one suggests smaller meshlets. Larger meshlets might have the advantage that they have less border vertices in total. So you might need to do less work. And in our experiments, this proved to be a very good balance. The other configuration might have more border vertices, and this means that you have to do more work. However, a single thread group needs less resources. And if your occupancy is limited by concurrent workload, smaller thread groups might actually be more beneficial for performance because it's easier for the scheduler to get the thread group launched. So the recommendation is that you should try out both configurations and just measure what's better for your specific case. For the second configuration, you can do another test actually. You can also try out a thread group size of 128. This would ensure that you have one thread processing one primitive. In certain scenarios, this might also help performance. Of course, you cannot do the same test with the other configuration because the maximum thread group size is 128, so you cannot double it. I have a small bonus question for you, and if you paid attention to the previous slide, the answer should be easy for you. The question is, how should you export the primitives for these configurations? The answer is that you should use the thread group sided stride. So for the first configuration, you should export to the indices thread ID and thread ID plus 128. And for the second configuration, you use thread ID and thread ID plus 64. Now let's move on to the last topic about mesh shaders specifically. In mesh shaders, you can also do triangle culling. This might help if the fixed function cull rate is the bottleneck. And if you do decide to do culling in your mesh shader, you can do it in two different ways. You can manually cull. This can be done before set mesh output counts. And this also means that no space for the vertex attributes is allocated. However, you need to fix the export indices. The second option is that you use svcull primitive. This has no effect on set mesh output counts, and this also means that the space for the vertex attributes is still allocated. However, you don't need to fix any export indices. Please note that the export space is always allocated for the maximum number of primitives, regardless of set mesh output counts. So in our experiments, svcull primitive proved to be more beneficial. This is because in our experiments, we were not limited by the amount of data that needs to get shared between the two stages. So by having not this overhead of fixing the export indices, we saw a better benefit. However, the other option, to cull manually, might be interesting if you have very fat vertices. If you have very fat vertices, you might also want to look at per primitive attributes. An example of where they could be used was presented by Max earlier when he talked about rendering quadrilateral primitives. Now let's move on to amplification shaders. Amplification shaders can also be used for culling, but they would cull an entire meshlet. And this can help performance as well, as we've seen earlier in the presentation. However, amplification shaders, they do add some latency to the rendering process, because the mesh shader draw calls are executed in the same order as the amplification shader thread groups were launched, and this is required to comply with the specified rasterization order. To hide this latency, amplification shader thread groups need to launch enough mesh shader thread groups, otherwise you will see gaps in your workload. And these gaps can be spotted in RGP under the waveform occupancy tab. The amplification shaders are executed on the async queue, so that's why you will also see them on the async queue in RGP. And the mesh shaders will be shown on the graphics queue. If you see gaps in your mesh shader workload, this might indicate that you're not launching enough mesh shader thread groups from your amplification shader thread group. Our recommendation is to launch at least 32 mesh shader thread group from a single amplification shader thread group. If you have smaller mesh shader thread groups, so for example, if you're using a mesh shader thread group of size 64 instead of 128, you might want to increase that number even. So in this case, a single amplification shader thread group should launch at least 64 mesh shader thread groups. If you're using amplification shaders to cull meshlets, you should try to process at least 32 or 64 meshlets per amplification shader thread group. You can also use the amplification shader thread groups to select dynamically the level of detail. And on this slide, I have a small example of how to not do it. So amplification shaders were used in this example to select dynamically the LOD and also possibly cull. And the strategy was to have one amplification shader call per mesh. The problem was that each mesh only spawned a few mesh shader draws, if any. So you had only one amplification shader thread group per mesh, and this amplification shader thread group only had a few threads active. So you ended up having a lot of amplification shader thread groups doing very little work and producing very little work. We tried to estimate the overhead of the amplification shader workload alone by changing the code to just cull all the meshlets. And we could see that the amplification shader workload alone took, well, in this very extreme example, it took 35 milliseconds. While this is a very extreme example, it highlights very well that it's very important that the amplification shader thread groups launch enough mesh shader thread groups. Lastly, amplification shaders can also have a payload. This is to pass on data to the mesh shader thread groups that it's launching. Payload is stored in group shared memory because every thread in the amplification shader thread group can read and write from it. Once the amplification shader thread group is finished, the payload is copied to a ring buffer. This copy can be quite slow because every thread is doing the copy, and the payload can take up to 16 kilobytes. It also requires a lot of VGPRs because what's happening is that the payload gets loaded from group shared memory into VGPRs, and then from the VGPRs it gets copied to the ring buffer using a buffer store. You can see this in the ISA actually. So the recommendation is to use as little payload as possible. And this concludes the section about performance recommendations. Now, let's have a brief look into the future of the geometry pipeline. In the past, we had the vertex shader pipeline. It has been around for many years now. Today, we also have the mesh shader pipeline. And recently, it gained a lot of attraction actually. But what will we have in the future? And you actually might have already heard of it. Because mesh shaders are coming to GPU work graphs. So it will be possible to launch mesh shaders from another shader. You can do multiple amplifications, which is not possible when you're using amplification shaders because they allow only for a single level of amplification. So you can do classification and then coalescing, and you can have multiple PSOs. So GPU-driven rendering is becoming much more flexible and is now also supporting draw calls with mesh shaders. This concludes the mesh shader talk. So we've seen that mesh shaders are a new way to process geometry. They are much closer to the underlying hardware and also give more control in how we use this hardware to process our geometry. We can do things that were previously not possible. For example, we can compress our assets in a way that we couldn't do when using vertex shaders. We can also process any type of primitives. And we can use mesh shaders to procedurally generate geometry in an efficient way. If you decide to use mesh shaders, you should pay attention to how you generate your meshlets and how you export your vertices and primitives. If you decide to use amplification shaders, make sure that your single amplification shader thread group is launching enough mesh shader thread groups. And this is the end of the presentation. I want to express my thanks to these people, because without them, this mesh shader presentation would not have been possible. And if you still want to know more about mesh shaders, I recommend to go to gpopen.com, because we have a blog post series about mesh shaders that contain even more information than this presentation. With this, thank you.